So the last point I would like to discuss. So according to Born-Oppenheimer approximation, the total energy of the system is the sum of translational energy, rotational energy, vibrational energy, and electronic energy. So now you can see the electronic energy is the highest, and if you want me to present in the decreasing order of energy, electronic energy, then vibrational energy, rotational energy, and translational energy. So this is the decreasing order. So the translation energy is the least, where the electronic energy is the highest. That is why I have said rotational energy changes are observed in microwave region, vibrational energy changes are observed in infrared region, electronic energy changes are observed in visible and ultraviolet region. So for the atomic gases, I have already told you what are atomic gases. They can be considered as a single particle. A single particle cannot rotate. Even if they rotate about any axis, the rotation involves very small energy. Even that make energy required to make it rotate is much smaller than the translational energy. It is negligible, highly negligible. Similarly, as an atomic gas or a single particle is not having any bond, it is not vibrating. So vibration is only in the case of bonds, bond vibration. So I can say the translational energy is the total energy of a single atomic gas. So the translation in three axes will contribute an amount of 3 by 2 kT. So this is called a gaseous statement. What is gaseous statement? For an atomic gas, when it is considered as a single particle, its total energy is translational. Total energy is translational. That translational energy is in three modes or in three directions. So each direction, the translation motion is contributing an amount of half kT to the total system. So the total energy of an atomic gas is 3 by 2 kT. If n atoms are present in the molecule, then the linear molecule has 3n minus 5 vibrational contributions, and nonlinear molecules have 3n minus 6 vibrational contributions. So when you want to measure the heat capacity of the gas at a constant volume, it is dou E by dou T at a constant volume. So the CV total, the total heat capacity at a constant volume is equal to heat capacity contributed by the translational motion plus heat capacity contributed by the rotational motion and heat capacity contributed by the vibrational motion. So everything is summed up. So each degree of freedom contributes a half kT. Each vibrational degrees of freedom contributes a kT to the total system. But what happens when you measure the heat capacity at low temperature and high temperatures? See, what is heat capacity? It is the quantity of the heat energy required to rise the temperature of a body by 1 degree. Suppose I take minus 100 degree and I want to rise the temperature by 1 degree, means I want to rise the temperature to minus 99 degree. At the same time, I take a system at 1000 degrees centigrade and I want to rise the temperature to 1001 degree. So both are 1 degree rise. But if you measure the heat capacity, there is a difference. Why this difference? Because it generally states that the heat energy required to rise the temperature by 1 degree. But this 1 degree rise, if it is observed in lower temperatures, it is different from what is observed in the higher temperature. Why this difference? That is what is actually the discussion. An approximation is made that at a room temperature, the contribution to the CV from vibrational motion is only 20%, which means that the vibrational contribution to the total heat capacity of the system is frozen at low temperatures. But the vibrational contribution becomes predominant at high temperatures. So when you rise the temperature, the vibrational contribution increases. but at a low temperature, the vibrational contribution decreases. So the vibrational contribution is making the difference in the heat capacity at the low and the high temperatures. So this is what we are seeing today.